All right. Welcome everybody to the ATRN seminar. Today we have Michael Lesnick that will talk about the stability of two-parameter persistent homology. Take it away.
Great, thank you very much. And thanks to all the organizers for the invitation and also for all the really good things that you guys are doing with the research network. I think you guys are doing some really valuable things and things that are all the more valuable considering that we're in a pandemic where people can't meet in person. So I'm going to be talking today about work with Andrew Blumberg on the stability of two-parameter persistent homology. The paper has actually been up on the archive for a while. We put it up in late 2020, but this is the first time that I'm giving a public talk on this. So I'm excited to share the ideas with you. Let's begin talking about one-parameter persistence and stability. So in TDA, we have several famous filtrations built from point cloud data that come up over and over again. The offset filtration, otherwise known as the union of balls filtration, the Čech and Rips filtrations, and the alpha filtrations are the main examples. And for each of these, we have a very clean Lipschitz continuity result, a stability result. So this work focuses on establishing closely analogous stability results for density sensitive bifiltration. So this is about an analogy between the one parameter setting and the two parameter setting. The bifiltrations that we're going to consider in this work required no parameter choices, and our results, or at least some of the results, guarantee robustness of these bifiltrations to outliers in a fairly strong sense, and something that we don't have for these bifiltrations, or rather for these filtrations in the one parameter setting. And we're going to see that these results reveal a tension between robustness on the one hand and computability on the other hand. The bifiltrations that we have that have the best robustness properties, we know the least about computing right now. And conversely, the bifiltrations that we can compute, we have only the weakest robustness results, or the most limited understanding of robustness so far. So it turns out that there's a really close analogy between the one and two parameter settings. And some aspects of this analogy are given in this table over here. And so everything in this table here appears in prior work. And what's new in our work is to fit all these guys in this table together, or especially the guys in the third column, into novel stability results for two parameter persistent homology that are closely analogous to what we have in the one parameter setting. So in the one parameter setting, as I mentioned, we consider the offset filtration. Its analog in the two parameter setting is the multicover bifiltration, the analog of the Rips filtration in the one parameter setting. In fact, we have two that we'll talk about, the subdivision and degree bifiltrations. And there's also an analog of the alpha filtration called the Rhomboid Bifiltration. So to formulate stability results in the one parameter setting, we need metrics on our data and metrics on our barcodes. And we're going to need analogs of these in the two parameter setting as well. And it turns out that there is a very natural measure theoretic analog of the Hausdorff distance in the, that we'll work with in the two parameter setting called the Progerov distance. And we'll also consider the Wasserstein distance, which is popular in TDA. And just as we have a Gromof version of the Hausdorff distance, the Gromof-Hausdorff distance, that allows us to talk about the distance between metric spaces that aren't embedded in a common metric space. We have a Gromof version of the Progerov distance that will allow us to compare measures on different metric spaces. And our analog of the bottleneck distance will be the interleaving distance, or its homotopy theoretic analog, the homotopy interleaving distance. And this analogy is justified somehow, or embodied, I'll say, by the isometry theorem. And then at least one way of getting stability in the one parameter setting is to use the Nerve Theorem. And here we're going to consider a close analog of the Nerve Theorem called the multicover Nerve Theorem. So I haven't given you references. Most of these ideas come from work that I was not involved in, but as the talk proceeds, I'll tell you where these nice ideas came from. Okay, so this is a this is our analogy, at least in part. So why do we care, though, about bipersistence of point cloud data? Why do we want to look at density sensitive bifiltrations? Well, the stability theory for one parameter persistent homology is really useful for a lot of things, but it has its limitations. It tells us nothing about robustness with respect to outliers. And indeed, it's very well known that standard persistent homology is not robust to outliers. And relatedly, it can be insensitive to structure in high density regions of our data. And this is illustrated here. We've got a point cloud circle, all TDA researchers' favorite picture. And we see that when we add just a few outliers in there, well, the circle is still clearly present. You can see it with your eyes, but those outliers really change the first persistence barcode of the data a lot. And you don't get a long interval seeing this cycle. Okay, this barcode looks somewhat similar to the one coming from a data set that has no loop at all in it. So these are serious issues because we want to apply persistent homology in the study of noisy data, and these standard constructions don't do so well. So this is something people have thought a lot about, and many solutions have been proposed using one parameter persistence. And I'll tell you about the ones that I know. So first, in early work on TDA, Gunnar Carlson's group was studying natural scene statistics, and they encountered this very problem. They had data with interesting structure in the high density regions, but that structure was somehow corrupted by low density noise. And so they removed the outliers by putting a density function on the data and just removing points whose density was below a threshold that they chose. Another approach that appeared in work of Chazal and company from 2009 is to fix a scale parameter, say for a Vietoris-Rips complex, and then filter by a density function. Okay, so fixed scale, varied density. And also density functions and their sublevel sets, or rather super level sets, were used in a TDA framework in work of Bei Wang and Jeff Phillips on what they call the kernel distance. And there's also an approach by Chazal and company that has that's gotten a lot of attention called distance to measure, where roughly speaking, what they do is they replace the distance function to a point cloud with a sort of smooth version that is sensitive to measure. And then a last approach in a somewhat different direction is to not just consider the barcode of a single point cloud, but rather not just consider the single barcode of a point cloud, but instead take subsamples of that point cloud and consider the distribution of barcodes of that subsample. And to my knowledge, this was first explored in work by Andrew Blumberg, Mike Mandel, and their co-authors several years ago. Okay, so there's a lot of work in this direction, as I say, and these are useful ideas. People have used these kinds of filtrations and these ideas in the practical study of data, and a number of these methods come with nice theoretical guarantees. So these are good and important ideas in TDA, but nevertheless, they share some common disadvantages. So here's what they are. First, each of these approaches depends on either one or two parameters that have to be fixed before you can do persistence. And in all cases, you can think of these parameters either as a scale or as a density threshold. And there aren't universal choices for these parameters. The suitable choice depends on your data, and maybe unclear a priori how to select these parameters. And if your data exhibits interesting features across a range of density, a range of densities and scales, it may be that no single choice of parameter can capture all the structure of interest in your data. Okay, so these are drawbacks to these one parameter approaches. And another drawback to these approaches is that if we fix a scale parameter, then we're not going to be able to see the feature scale of we're not going to be able to see the scale of the homology features. And this is something we like a lot about one parameter persistence, right? Like we like that we can detect the small holes from the big holes. And so we lose this if we fix a scale parameter. And on the other hand, if we fix a density parameter, we're not going to be able to distinguish low density features from high density features. And that may be something that we want to do in cases where there's some heterogeneity in density in our data. So all of this motivates us to consider bifiltrations, where the basic idea is that we're going to treat both scale and density as persistence parameters, rather than just scale as in the traditional case. Okay, so in two-parameter persistent homology, you start with a data object, say a point cloud, and from that you construct a bifiltration, and then usually you take homology with coefficients in a field, and this gives you an algebraic object called a bipersistence module. And it's well known that defining the barcode of a bipersistence module is problematic. We don't have a good, we don't have a completely satisfactory notion of a 2D barcode. So if we're going to develop stability theory in this setting, the natural thing to consider is how similarities between data objects descend down to similarities between the bipersistence modules, okay, to work directly on the algebraic level. Now, in fact, we can go somehow one step further up this pipeline and work directly on the level of the bifiltrations. And that's what we're going to do here. We're going to worry about this arrow, worry about how similarities between data objects descend to similarities between bifiltrations, and those stability results will yield ones on the algebraic level as trivial corollaries. So let me start by telling you what a bifiltration is to me. Now, suppose I'm given totally ordered sets S and T. Then I can define a poset structure on their Cartesian product by taking x1, x2 less than or equal to y1, y2, if and only if x1 is less than or equal to y1 and x2 is less than or equal to y2. And so here are my definitions of a filtration and a bifiltration. So for T, a totally ordered set, a filtration is just a functor F from T to topological spaces that's increasing. So in other words, FR is a subset of Fs whenever R is less than or equal to S. And then similarly, an S by T index bifiltration is a functor F from this Cartesian product to topological spaces such that FR sits inside of Fs where R is less than or equal to S. So it looks exactly the same, this line and this line, but now we're just looking at the partial order on this Cartesian product down here. So I think this is the most convenient definition of a bifiltration for general stuff in multi-parameter persistence or two-parameter persistence. But in this work, we're just going to consider these fixed choices of S and T. We'll take S to be the opposite poset of positive reals, T to be the poset of positive reals. And those are convenient choices sort of for technical reasons. And we want to talk about what it means for two bifiltrations to be the same up to homotopy. And for this, we'll use the language of weak equivalence. So a natural transformation of bifiltrations, gamma, say from F to G, we say is an object-wise homotopy equivalence if gamma A, the component of gamma at index A, which is just a continuous map from FA to GA, is a homotopy equivalence. Okay, so if all these guys as A varies are homotopy equivalences, we have an object-wise homotopy equivalence. Now, sometimes when you're doing homotopy theory, I'll say often, it's more convenient for technical reasons to consider object-wise weak homotopy equivalences, but I won't worry about such things here. And in any case, these notions coincide by the Whitehead theorem if all your FA and GA are homotopy equivalent to CW complexes. So, okay, now we've got our notion of object-wise homotopy equivalence, and we say that F is weakly equivalent to G. The point is this notion is going to generate an equivalence relation as follows. F is weakly equivalent to G, which we write like this: if there's a zigzag of object-wise homotopy equivalences connecting F and G. And to think about, so by the way, this is a standard notion of equivalence in homotopy theory. And to understand why this might be appropriate in TDA, it's helpful to think about the Nerve theorem. So if you think about, say, 2 points in R, their union of balls filtration and their nerve, their associated nerve filtration, say using open balls, then those two filtrations are weakly equivalent in this sense, but there's not going to be an object-wise homotopy equivalence from the nerve filtration to the union of balls filtration. I mean, it's something to think about, but essentially for continuity reasons, you don't have such a map. And so that suggests some kind of asymmetry in this notion, which you might want to correct via zigzag. And that's what we do. Now you can find an example of two spaces, two filtrations that are weakly equivalent, but there's no arrow in both directions using the same idea. Okay, so we'll come back to weak equivalence later, but now we're going to talk about some constructions for going from data to a bifiltration. And as I've already indicated, there are several constructions for this. So the first that appeared in the TDA literature was due to Carlson and Zomerodian. I call it the density RIPS bifiltration. So here is similar to things we discussed before. You have a data set and you put a density function on it. And now one of your filtration parameters thresholds by density, and the other one is just the ordinary scale parameter for, say, Viator's RIPS. And so this is a good construction, but its disadvantage is that it depends on a parameter, namely the bandwidth parameter for your density estimate. Like your density functions always are going to require a choice of scale. So if we're going to do complicated things with 2-parameter persistence, it would be nice not to have to fix any parameters. And happily, there are several very natural constructions that you can consider. So there's this multicover bifiltration, and it appeared in the TDA literature first in the work of Zhao and Sheehy from about 10 years ago. There's also a construction called the subdivision RIPS bifiltration due to Sheehy, and there's a construction called the degree RIPS bifiltration, which first appeared in my work with Matthew Wright. So I'm going to tell you about all of these, starting with the multicover bifiltration. And in explaining this stuff, it's more convenient to work with unnormalized versions of these objects, but when we talk about probability theory and things like this, we want to work with normalized versions. So let me start by talking about the unnormalized multicover bifiltration, which I'll denote over here. I'll denote it tilde m, and we define it like this. So at parameter k comma r. So let me say first of all that we're looking at a subset of Euclidean space X, and at k parameter r, this bifiltration is the following space. This is the subset of Rn consisting of all points y, such that there exist k points in X whose distance to y is less than r. And sometimes people put a less than or equals here, but it doesn't matter. This is a technicality. And so it's convenient for me to use a less than here, though. So for example, if r is the radius of these balls drawn in this picture, and the points are these white dots here, then the multicover bifiltration at this radius parameter in k equals 2 is just the set of points in the plane that are covered by at least 2 balls. And similarly, the multicover bifiltration at parameter k equals 3 is a set of points covered by at least 3 balls. Okay, so when you take k equals 1, you recover the usual union of balls filtration. So this is indeed some kind of a density sensitive refinement of that. And then to normalize this, we just change the definition by sticking a size of x over here. Okay, so we're essentially just rescaling things in this k parameter. And now that's the multicover bifiltration. So next we move on to the subdivision bifiltration, subdivision RIPS in particular. So given a metric space X, I'm going to let Rx denote its RIPS filtration in the next slide. And here's the idea of the subdivision bifiltrations, again, due to Sheehy. And I think this is a really elegant idea, and it's simple too. So the key observation is that the barycentric subdivision of any simplicial complex T has a natural filtration structure on it. So here's how this goes. First, by the way the barycentric subdivision is defined, vertices of the barycentric subdivision correspond to simplices of T. Formally, they are simplices. Okay, and so by the way, here is a simplicial complex, and here is its barycentric subdivision. So for instance, this two face here corresponds to this vertex in the center of the barycentric subdivision. This edge corresponds to that vertex. And so now we're going to let the value of this filtration at index k be the maximal subcomplex of this barycentric subdivision whose vertices have dimension greater than or equal to k minus 1. And the minus 1 here is there for technical reasons. So that's the construction. So you see T1, I've got my indices as superscripts here by accident. They should be subscripts, but T1 is just the full barycentric subdivision because every vertex has degree at least 0. And then T2 is the maximal subcomplex that we get just by keeping the vertices that I'm kind of tracing out with my mouse there. You get this guy over here. And so now we're going to apply this to specific, well, I should say first, applying this index-wise to any filtration yields a bifiltration that I denote by sticking an F in front of the name of the filtration. And we're going to consider this for the case where F is a RIPS filtration. And in that case, we get the subdivision RIPS bifiltration. And this is indeed a density-sensitive refinement of the Viator's RIPS filtration. Why? Because if you look at vertices in the spaces of this subdivision RIPS bifiltration for large value of this parameter k, those correspond to clicks in the RIPS filtration, or rather, yeah, they correspond to clicks, and these clicks correspond, or these clicks essentially, yeah, they correspond to regions of high density in the data relative to your choice of scale parameter. So you're seeing something about density with this construction. And you also have a subdivision Czech version, just using the Czech filtration instead of RIPS. So let's have some notation for this. For X, a subset of Rn, let C of X denote the Czech bifiltration constructed using nerves of open balls, work with open balls for technical reasons, again. And now we have this very nice result due to Sheehy and then also to Sheehy and Kavana, which says that for X, any finite subset of Rn, the subdivision Czech filtration of X is weakly equivalent to the multicover filtration of X. So Sheehy had a version of this result back in 2012 for fixed values of the parameter k and allowing the radius to vary. And then with Kavana, they extended this to varying values of k as well. And the way that they carried out this extension was by observing that somewhat charmingly, I think, the proof of this multicover nerve theorem is actually implicit in the standard proof of the nerve theorem that you see in Hatcher, for example, this well-known version. I was told that it goes back to Vail, this proof. And so in fact, there is an additional step which was omitted in this this reference that you need to get this extension. It's essentially a homotopy finality argument and involves some kind of statement about homotopy colimits. But yeah, once you fill in that little step, the proof is sort of already hiding in the standard proof. And this is nice because now we have a explicit simplicial model of this multicover filtration, which is nice. But on the other hand, these subdivision bifiltrations are huge, right? Both the subdivision Czech and subdivision RIPS have exponentially many vertices in the size of the point cloud X. And so that's an obstacle to using them directly in practice. But nevertheless, I think they're very interesting. And so we're going to study them here. That's going to be part of what we do and what follows. But I need to tell you about the degree bifiltrations before we get to that. So this is a construction that's a lot smaller than the subdivision bifiltrations, and I think also is elegant. So right, there's a simple general observation underlying this construction, which is that any simplicial complex is naturally filtered by vertex degree. We'll consider decreasing vertex degree here. This is essentially what's called the upper star filtration in TDA. in the special case of, I mean, we're looking at the upper star filtration now in the special case of vertex degree. And so applying this filtration construction index-wise to each simplicial complex in the simplicial filtration yields a bifiltration that will denote df. And so in the case where f is a Vietoris-Rips filtration, we call the resulting bifiltration the degree Rips bifiltration. And there's an example of it here on the slide for this point cloud down in the lower right corner. Okay, so specifically in this example, the degrees that I considered were 0 in this column, in which case you're just looking at some snapshots of the ordinary Rips filtration, degree 2 here, and degree 4 here. So for example, when you're in this column, all these vertices here have degree less than 2, so you get rid of them and you're just left with this, this little diamond here. And then when you get up to here, now these vertices do have degree 2, but they don't have degree 4, so they also get removed from over here. So that's the degree bifiltration. And this is also a density sensitive construction because degree of vertices in the Rips complex is a measure of density relative to your choice of scale parameter. Okay, that's all I have to say about bifiltrations for now. And so let's turn to metrics on bifiltrations. First, what is the Progerov distance, also known as the Progerov distance? So as I may have mentioned, this is a metric between probability measures mu and eta on a fixed metric space. And it's given by this big formula over here. So the Progerov distance between mu and eta is the supremum over all closed sets A in your metric space Z of the infimum of all delta satisfying the following big condition over here. And this big condition says that mu of A is less than or equal to eta of the thickening of A by delta plus delta, and then also symmetrically reversing the roles of eta and mu. And so this distance, if you're familiar with interleavings, this distance may remind you somehow of the definition of 2-parameter interleavings. And so maybe it's not surprising that you can relate this to interleavings. And that's exactly what we're going to do below. Let me first mention that there's a nice connection between this Progerov distance and the P-Wasserstein distance, which is as follows. So the Progerov distance is less than or equal to the minimum of the P-Wasserstein distance raised to the 1/2. And well, that's one term in the minimum, and the other one is the P-Wasserstein distance raised to the P over P plus 1. So that means that if I give any stability bound in terms of the Progerov distance, I'm going to get a corresponding bound in terms of the Wasserstein distance for free. Okay, so this bound here, like this is really 2 bounds stuck together using a minimum. This one is standard. You can find it in books. And this one, well, so Håvard Bjerkevik worked this out as part of a joint work that we have. And it's not a really hard proof. So we imagine that it must be known. It must be in a book somewhere, but we don't know a reference. So for now, Håvard gets credit. All right. So we're going to work with the Progerov distance from now on. But we, again, want to consider this extension to measures on different metric spaces, the Gromof-Progerov distance, which was introduced by Grevin and co-authors in 2009. So let mu and eta now be measures on metric spaces X and Y. Then the Gromof-Progerov distance between mu and eta is obtained as follows. We take our metric spaces X and Y and we isometrically embed them into a common metric space and consider the push forwards of the measures mu and eta under these 2 embeddings, take the Progerov distance of the push forwards, and then infimize over all pairs of embeddings. Okay, so this is very, very closely analogous to how we go from Hausdorff to Gromof-Hausdorff, as I said. And a property of both the Progerov and Gromov-Progerov distances that are critical, that is critical for our work, is that we have a strong robustness to outliers. So if Y is a finite metric space and X is a non-empty subset of Y, then the uniform probability measures of X and Y, which I'm denoting like this, mu X, mu Y, is greater than or equal to the number of points in Y that are not in X divided by the number of, excuse me, let me say this again. The number of points in Y, not in X, divided by the number of points in X is greater than or equal to the Progerov distance between these uniform measures, and that in turn is greater than or equal to the Gromov-Progerov distance between these uniform measures. And actually, this statement implies a corresponding statement for the normalized counting measures, for measures that live in Rn when your point clouds live in Rn, which is the case we care about most, I guess. Okay, so if I give you stability bounds in terms of either of these distances, we're going to interpret those as strong robustness results. Okay, so we're going to need interleavings on filtrations, and we need to define them in the setting of this indexing category here. And what's interesting here, and it's not that interesting, I suppose, but what's interesting is, and maybe I'll pull out my iPad to illustrate this. So, right, so our parameter space lives in R2 like this, and now our filtration directions are like that. You see what I'm doing there? Okay, so there's some kind of boundary of our parameter space that's kind of upper bounding. Well, the boundary technically isn't included because I'm just looking at positive real numbers here, but you have this kind of boundary, and in your definition of interleaving, you have to account for that somehow. And this slide explains in one technical way how to do that, I suppose. But maybe a simpler way of explaining it is that we're going to extend this bifiltration to all of R2 as follows. For stuff below, down here, we're just going to put copies of the empty set everywhere. And for stuff here in the second quadrant, we're going to put a point. Okay, and so now you've extended your filtrations indexed by pairs of positive real numbers to all of R op times R. And now your standard definition of two-parameter interleaving distance adapts immediately to this setting. Okay, usually you define it for R2 index persistence modules, and now one of the directions is flipped, but it doesn't matter. The same definition works, and that's what's explained on this slide. Okay, so now I have interleavings. I think that's all I want to say about it. I see I'm short on time. Okay, so we have a notion of homotopy interleaving that is obtained as follows. F and G are delta homotopy interleaved if there exist delta interleaved filtrations F prime weakly equivalent to F and G prime weakly equivalent to G. And then the homotopy interleaving distance on bifiltrations is given by taking the distance between F and G to be the infimum over all delta, such that F and G are delta homotopy interleaved. And maybe this distance is unfamiliar to many of you, but it turns out to be a well-behaved homotopy invariant distance on filtrations. In fact, it's the universal, meaning largest stable and homotopy invariant distance on multifiltrations. And that provides some justification for its use in the formulation of TDA theorems, like the ones we're about to see. So with that, we come to our main stability results. And as I think I said, these are one Lipschitz stability results that look a lot like the ones that we have in the one parameter case, except they're stated on the level of filtration. So first, for the multicover bifiltration, and here we're going to use normalized filtrations throughout. I didn't say anything explicitly about normalized subdivision RIPs, but we're considering that now by, I guess, slight abuse of notation relative to what we saw on an earlier slide. So let X and Y be finite subsets of Rn, and let eta X, eta Y be their normalized counting measures. And the first result is that the Progerov distance between these counting measures is greater than or equal to the homotopy interleaving distance between the multicover bifiltrations of X and Y. Okay, now, secondly, we have a result for finite metric spaces not necessarily equipped with an embedding. Call them X and Y, and let their uniform measures be mu X, mu Y like before. Then the Gromof-Progerov distance between mu X and mu Y is greater than or equal to the homotopy interleaving distance between the subdivision RIPS bifiltrations of X and Y. Okay, so this is like an analog of stability for the offset filtration. This is like an analog of stability for RIPS filtrations. And by the multicover nerve theorem, one also gives you a stability statement for subdivision Czech bifiltrations for free. Now, one is really easy to prove. There's actually not a lot to it. The main thing is to just figure out what the language is. And the proof of two is really closely analogous to the proof of stability for RIPS persistent homology that was first given. There's several proofs by now. The first one was due to Chazal and other co-authors in 2009. And their proof, well, our proof in close analogy to the other one, in the one parameter case, uses part one here, and then it uses the multicover nerve theorem, whereas the one parameter one would use the ordinary nerve theorem. And it uses a trick called the Kuratowski embedding, where you're going to take your data, you take your metric space and embed it in a L infinity space. Essentially, you're going to embed it isometrically in an L infinity space, and there you use the fact that Czech complexes and RIPS complexes are the same in such spaces. So you can now use the result for subdivision Czech bifiltrations to say something about subdivision RIPS. So that's the outline. So really the main new ingredient is using the multicover nerve theorem relative to this classical case in one parameter. All right. So now I want to tell you about stability for degree RIPS, but this gets a little more technical. So our narrative here in this work is that the clean stability results, the ones that look a lot like the one parameter case, are for the subdivision bifiltrations, as we just saw. And for degree RIPS, you can still say things that are analogous, but the statements are a lot weaker. And here we need to introduce some kind of affine interleaving, right? The ordinary interleavings are coming back to this picture. They involve maps that will go like that. Like you have a vector space in F at this index A, and it maps to a vector space in G at index A plus what I called vec delta in my earlier slide. So up and to the left. So you're just looking at these kinds of uniform translations up and to the left. Here, instead of looking at a uniform translation, we need to consider affine maps. So the relation between the source and target is going to be given by this affine map alpha C delta that's written over here. So in the first coordinate, you still just translate by delta, but now you need to multiply by your second coordinate by a parameter C and then add delta. So you're looking at these kinds of affine interleavings. And so, yeah, this is a lot of symbols, but C for what we're going to do is going to be 3. Okay, and so now you have an analogous notion of homotopy interleaving for these affine interleavings. And the statement about degree RIPS is that for any non-empty finite metric spaces, X and Y, the degree RIPS bifiltrations of X and Y are alpha 3 delta homotopy interleaved, right, in the sense of this slide over here. Okay, admittedly, I'm going a bit fast through through this, but they're affinely interleaved, where now your delta is your Gromof-Hausdorff distance between the uniform measures of your metric spaces. And so qualitatively, one way to think about this is, if you're familiar with one parameter persistent stability stuff, is that the relationship between these degree Rips bifiltrations for X and Y is analogous to the relationship not between the Rips filtrations of X and Y, but rather the Rips filtration of X and the Čech filtration of Y. Okay, because these are related by an affine interleaving. Okay, it's a much weaker notion of stability in the following sense. So in the following two senses, in fact. So first, we have a proposition, and this is actually the most technical thing in the whole paper, and it uses a result of Henry's on, right? Everybody knows Henry's computation of the Vietoris Rips persistence of points on a circle, right? So we use this, and we show that actually this proposition would be false if we reduce this constant 3 here. 3 is the multiplicative constant in your affine interleaving, which is really controlling how weak things are, and you can't do better. And we show this by construction. And so that's too bad. And the map from X to its Vietoris, to its degree Rips bifiltration also turns out to be discontinuous with respect to the Gromof-Progerov distance and the Homotopy interleaving distance. Okay, so the upshot, I would say, is that you have robustness in this setting that is considerably stronger than what you have in the one parameter setting for ordinary Vietoris Rips, but still a lot less strong than what you have for subdivision Rips or multicover bifiltration. Now, I have an example illustrating some of the stuff, but in the interest of time, let me skip it. If you're watching the video, then you can pause here, I suppose. But I do want to say that degree Rips does have a strong Lipschitz stability property of some kind, and this appears in work of Roll and Skokola, but that result is formulated with respect to different distances on the point clouds, and that doesn't accommodate addition and removal of outliers. Okay, so if you work with a more restrictive notion of distance, you can get stronger results. Okay, so I see we're at 44. I did want to say something about computation, but I wonder, should we maybe stop here and perhaps I can get to computation a little bit in answer to a question if anybody asks about that.
Yeah, that's probably a good idea to stop here, and then maybe people will ask about the computation. So yes, so before we get to questions, first of all, thank you, Michael, for the great talk. And I would like to ask everybody to unmute themselves and clap.
Thanks.
All right. So are there any questions?
Yeah, I have a question.
Go on.
Michael, you define the Gromof-Progerov distance between probability measures on 2 different metric spaces. But then after that, you refer to the Progerov distance between probability measures on 2 different metric spaces. And I didn't understand what that would mean.
Okay, so let's take a look and find out where you're talking about. Maybe you can help me. So we're talking about this slide?
Right, yeah, if you look, for example, just at the very bottom of that slide, you have the Gromof-Progerov distance, which makes sense, but then you have the Progerov distance, which I don't see how that would be. Does the definition of Progerov distance make sense for measures on different spaces?
No, but X is a subset of Y. So
I see. X is a sub. Okay, I got you. And so whenever you use the Progerov distance in that sense, one of the spaces is a subset of the other. Is that right?
Yeah, I mean, this is how we stated this in the paper. It's a bit of a funny way of stating what I'm trying to get at. I mean, it sort of carries the right substance, but really what I care about is 2 separate cases. I care about this case for the one that I've written down on the slide here for Gromof Progerov, and I care less about this bound, but this bound here, in the special case where X and Y are both embedded in Rn, this bound here implies what I care about, which is a corresponding bound like this for the normalized counting measures on the data sets. Okay, so I didn't want to introduce separately the uniform probability measure of X and Y and also the normalized counting measure. So I wrote it down like this.
Oh, I see. And at the bottom there, I see you have the set theoretic distance between Y and X, which sort of implies that X is a subset of Y. Okay.
Does that answer your question, Stephen, or do you have more questions?
No, that answers my question. Thank you.
Oh, perfect. Are there any other questions?
I'll just ask or say a quick comment and then a question. So the quick comment, Stephen, is that another spot, Michael had measures on X and Y, but they were both embedded in Rn.
Right.
So a priori, they're sort of like measures on different X and Y, but they both give measures on Rn.
Yeah, that makes sense.
Right, yeah. But Michael, I'll ask you if you could say a little bit about computation.
Thank you for taking the bait. Okay, so I mean, I'm going to try to say a little bit without finishing the talk, because I think that would be too much. I still have a few slides left here. So first, what is the computational problem? Well, in applications, you want to work with the persistent homology of these bifiltrations. But if we can get at the bifiltration itself, then we now have efficient methods for computing minimal presentations of these homology modules, and we can extract whatever invariants out of these minimal presentations that we would like, or we could use them to compute distances. So we focus here on just computing the bifiltration or one weakly equivalent to it. And so I want to say something quickly about the computation of the multicover bifiltration. So you've got the simplicial model, as I said, this subdivision check, but it's too big to work with. But interestingly, there's also another combinatorial model of the multicover bifiltration called the Rhomboid Bifiltration, which was introduced recently by Edelsbrunner and Osang. And it's sort of implicit in that earlier work that, or at least kind of seems likely from that earlier work, that the Rhomboid bifiltration is going to be weakly equivalent to the multicover bifiltration. And so with 3 other authors, I proved such a thing recently, or I'll say we proved it. And so now you have a smaller model. This rhomboid bifiltration is a polyhedral model in Rn+1, and it's a lot smaller than the subdivision check. So specifically, it has O of the size of X raised to the n+1 polyhedra when X lives in Rn, and can be computed in linear time in the size of the output using an algorithm of Edelsbrunner and Osang. So Osang has an implementation, and he's been able to handle, say, 200 points in R3 for the full bifiltration. And they can also do handle bigger data sets if they're not computing the full bifiltration. So this is, I think, for people like me who are interested in computation, this is exciting, because this is like just below the threshold of practical utility, right? You can compute something, but we're not quite there. So maybe with approximate computation, we're going to be able to really get into the realm of practicality. I mean, that's a subject for future work. Okay, so now for data in high dimensional space, I have no idea how you would do something with the multicover bifiltration, but you also can compute the degree RIPS bifiltration. This is implemented, for example, in software called Rivet that I've worked on with other people. And these computations are, they still can get expensive, but if you coarsen your biopersistence module a little bit, then you can compute the low dimensional skeleton of these degree RIPS bifiltrations well enough to really look at practical data with these guys. And I'll show you a picture in 1 second. And then finally, for the subdivision RIPS bifiltration, essentially nothing is known about computation, which is, I think, intriguing. Right? So again, you're not going to be able to compute this guy directly, but maybe you can compute its homotopy type, perhaps for data with low doubling dimension, or maybe you can compute it approximately at least. These are completely open questions. And not only has nobody solved them, I don't know if anybody's even thought about them. And I think these are good questions. So anyway, this illustrates what I said at the beginning of the talk, which is that we have a tension between computability and robustness, right? For example, subdivision is really robust. We know nothing about computing it. Degree RIPS bifiltrations are computable, but we only have these weaker robustness results. And I think there's progress on both ends as far as understanding computability more and hopefully getting some positive results. But also experiments seem to suggest that there may be more to the robustness of degree RIPS than my results with Andrew that I gave before express, and maybe interleavings aren't the right language for this. This is a sort of intuition I have for this. So I know I'm giving you a long answer, Henry, but let me show you.
But Michael, this is mainly, so sorry, is it mainly for like subsets of planes over like a plane, or, you know, if you like the dimension of the point cloud is growing, it's right, it's the.
So when you say this, which bifiltration are you referring to?
No, let's say the bifiltration that you were looking at. Exactly.
Okay, so yeah, so for the rhomboid bifiltration that I just mentioned, so I showed you the size.
Right. Yeah. So that's the smaller version of the exactly of your version. So does it work, for example, if I have a point cloud in R5?
I'll tell you that the mathematics works out, the objects get bigger, and the implementation that Georg has works only for n equals 2 or 3. I wrote that on the slide.
Okay. So okay. All right. Okay.
But I think that's just a matter of engineering. Like there's no serious obstacles, but I think it would probably be very expensive to handle R5 with construction, but maybe with another construction it can work. Now, as far the story is very different for degree RIPS, right? Just like ordinary RIPS, like you can handle, you don't care so much about the dimension of the data, but then for large radius parameters, everything gets connected and things get expensive. So, I mean, just to show you something that we can do that's practical, at least using 0th persistent homology, we computed the degree RIPS bifiltration of about 1,100 HIV genomes. I mean, they're pre-aligned and the Hamming distance is used on the aligned genomes. And we do a little bit of coarsening, not too much. And so we can see some rich cluster structure in this data as illustrated here. I haven't gone through, this is a screenshot of Rivet. I haven't gone through the details of what we're seeing, but you're able to see rich cluster structure here in a way that is completely parameter free insofar as like you haven't fixed any parameters that might bias the results. And so I think that suggests that, I mean, this picture suggests two things to me. One, although there's room for computational progress with degree RIPS bifiltrations for sure, there's a lot of room, I think. You already can do something that's interesting and that's different than what's been done before. And two, in spite of the weakness of these robustness results in some practical data, you may be able to see interesting structure, and that phenomenon is something that I'd like to understand better.
All right, are there any more questions? If not, then let's thank Michael again. And I will stop the recording now, and you can still ask some questions to Michael afterwards.